Dear students, in the previous sections, we have introduced the concept of sampling distribution by using arithmetic mean as the estimate. Specifically, we have derived the mean mu of x bar as equal to mu of x and standard deviation of x bar as equal to sigma by root n. And as you can see, the standard deviation of x bar is smaller than the standard deviation of x. Now we consider what is the exact shape of the distribution of x bar. What is the exact shape of the distribution of x bar? We consider two cases. First, we consider the sampling distribution of the sample mean when the sample is taken from a normally distributed population X. Suppose that the variable under consideration is normally distributed. Say, for example, height of the population, normally distributed. And to make an inference about the average height, we take a sample from this population. That is sampling distribution of the sample mean when the population is normally distributed. Now, the result is, if the variable under consideration is normally distributed, then x bar is also normally distributed. If x is normally distributed, if height of the population is normally distributed, distribution of x bar is also normally distributed. Now, in the form of a definition, suppose that a variable x of a population is normally distributed with the mean mu, and let me write it like this: normally distributed with the mean mu and variance sigma square. Variance sigma square, standard deviation sigma. Then for the sample size n, the variable x bar is also normally distributed with the same mean and variance sigma square by n, or standard deviation sigma by root n. So, if x is normally distributed with the mean mu and variance sigma square, x bar is also normally distributed with the same mean and variance sigma square by n. As an example, consider the variable IQ, which we have discussed earlier, IQ, and suppose that IQ is normal with the mean 100 and standard deviation equal to 60. Standard deviation, this is variance, root of variance is standard deviation. Now, the distribution of IQ is normal with the mean 100 and standard deviation 60. So that most of the observations will be between 52 and 148. Now, let us consider the distribution of x bar for n is equal to 4. N is equal to 4. Then the distribution of x bar is something like this. With the mean 100 itself, mean is same mean, n is equal to 4, The standard deviation is sigma by root n is equal to 16 by root 4 is equal to 8. So the distribution of x bar, this is the distribution of x with what is known as 108 sigma by root n. Now suppose that you take the n is equal to say 16, then 16 by root of 16 is equal to 4. Root n is equal to 60. Then the distribution has a shape like this. 100, again mean is 100. So as you can see, x is normally distributed. The distribution of x bar is also normally distributed. Mean is the same, but as sample size increases, you can see that the standard error decreases. So the distribution of x bar concentrates more and more towards the mean 100. That is the standard error. The sampling error decreases as the sample size increases. Now, let me generalize. If the population is normal, the distribution of x bar is normal, irrespective of the sample size. Irrespective of the sample size. Now suppose that the population is not normal. The population is not normal. Now what about the distribution of x bar? If x is not normally distributed, again x bar is normally distributed provided that sample size is sufficiently large. If x is not normal, or if the distribution of x is unknown, what about the distribution of x bar? Again, the distribution of x bar is normal provided that sample size is sufficiently large. Sufficiently large means n greater than or equal to 30. This remarkable result is known as central limit theorem. Central limit theorem, CLT. So if you cannot assume that population is not normal, again you can assume that the distribution of x bar is normal provided that you have n greater than or equal to 30. Let me define it more formally. For a relatively large sample size, the variable x bar is approximately normally distributed regardless of the distribution of the variable under consideration. The approximation becomes better with the increasing sample size. And this result is central limit theorem. And to conclude, let us conclude what we have stated about sampling distribution so far. 1. Mu of x bar is equal to mu always. 2. Sigma of x bar is sigma by root n. 3. If x is normal, then x bar is also normal. Then for sufficiently large sample size, x bar is normal regardless of the distribution of x. Regardless of the distribution of x. These are the points you should remember always. And let me give a graphic representation of these results. Now, suppose that this is the distribution of x normal. The distribution of x normal. X is normally distributed, symmetric, bell-shaped. So n is equal to 2. Distribution of x bar is like this. N is equal to 10. The distribution of x bar is like this. Then n is equal to 30. The distribution of x bar is like this. So the spread of the distribution of x bar decreases as the sample size increases, but the position of mu is same. Now, suppose that the distribution of x is like this. For n is equal to 2, the distribution of x bar is skewed. When n becomes 10, it is still a little skewed like this. But when n is equal to 30, it becomes normal. Now suppose that the distribution of x is uniform like this. Like this. Then for n is equal to 2, the distribution of x bar is like this. For 10, it is like this. For 30, it is like this. Now, as you can see, whatever is the shape of the distribution of x, the distribution of x bar is normal for n 30 or greater. But if x is normal, distribution of x bar is always normal. Always normal. So, let me conclude with a few notations. The notations are, if x is normal, if x is distributed as normal with mean mu and variance sigma square, x bar is also normal with mean mu and variance sigma square by n, then z is equal to x minus mu by sigma normal with the 0 and 1, a standard normal distribution. X is converted into z. You can convert x bar also into z as z is equal to x bar minus mu by sigma by root n normal with the 0 and 1. Conversion of x bar into z. And remember this. This is the formula which we use in hypothesis testing. That is, x bar is used to estimate the parameter mu. But estimator is not directly used for hypothesis testing. We convert x bar into a test statistics. X bar is a statistics estimator. It is converted into a test statistics z, and z is used for hypothesis testing, provided that sigma is known. And in most cases, sigma will be unknown, so we will replace sigma with s, sample standard deviation. Then z will be converted into another distribution t as x bar minus mu by s by root n. It is a t distribution with the degrees of freedom, etc., concepts which we will see later. So remember this. This test statistics is used to test the significance of mu if sigma is known. Otherwise, we use t statistics, points which we will see later. So this is the sampling distribution, and the sampling distribution is used for hypothesis testing. And remember also, x not normal with the mu and sigma square. Again, x bar is normal with mu and sigma square by n as n approaches to infinity. Technically, we say n approaches to infinity means n greater than 30. N greater than 30. Again, even though x is not normal, as x bar is normal, z is equal to x bar minus mu by sigma by root. Normal with the... So normality is of the population is not a problem for hypothesis testing if you have sufficiently large sample size. Points which we will see later.